Okay, thank you very much, everyone, for joining this talk. I'm going to share with you the latest advances on my side of this project that is funded by the CDBP. Is about the application of satellite technology to infrastructure monitoring, and more specifically, this talk is about multi-temporal InSAR data analysis with the structural health monitoring application. You know that there exists a wide range of different sensors on satellites that are collecting data from the surface of the Earth. Maybe you are more familiar with the traditional optic color images like Google Maps, these type of things, but there are a wide range of other different sensors, for instance, multispectral, that they gather light reflected by the surface of the Earth in many different wavelength channels and with multiple and different applications. For infrastructure monitoring, there is one particular type of technology that is very useful in this case, which is interferometric synthetic aperture radar, which allow us to measure very little displacements on the objects observed on the line of sight of the sensor. What happens in SAR images is that the satellites emit a signal. This signal is backscattered by the different objects on the surface of the Earth, and then we receive the backscatter signal, we form an image. In fact, because the signal has two properties, amplitude and phase, what we get is two different images. One is the amplitude image, which is something similar to what you can observe in the top right figure, something close to what a black and white image. And then we have the phase image. If you see by an image of phase alone, you won't be able to get any useful information from that. But when you combine two different phase images from two different acquisitions at different times from the same place in a process that is called interferometry, it is possible to estimate the displacements of the objects that we are observing by that explain the observed difference in the phase of these two images. So by doing this interferometry process consistently over time on the different acquisitions of the satellite, it is possible to obtain a time series of displacements of the different objects that we are observing, and this is what we want to use for infrastructure monitoring. For instance, this is one particular example of application of this technology called multi-temporal InSAR. What we are going to obtain is for each point that backscatter consistently the signal from the satellite, we are going to obtain a time series of displacements. So, for instance, we can, in this particular example, we can observe some time series corresponding to the bank metro station where there have been some tunneling activities, and we can use this time series of displacement to study the settlement of on this region. Regarding the data, we have different satellites where we can get SAR data to do this process. On one hand, we have the free available data provided by the Copernicus program from the European Space Agency. They have a satellite that is called Sentinel-1, and they provide the data freely. The spatial resolution of this is 5 × 20 meters, and the revisit time is 6 days. On the other hand, we have commercial missions that you will have to pay a service fee to task an operation, but in this case you will be able to get a much higher spatial resolution. For instance, TerraSAR-X is up to, and Cosmos SkyMed are two examples of these satellites, and you can get spatial resolution up to 0.5 square meters. And the time revisit of these satellites is between 11 days and up to 4 days. So if we want to explore large areas and study large areas at scale, it is not feasible to do it manually because the large amount of data that these satellites are acquiring. So there is a clear need for automatic ways of evaluating this and analyzing this time series of displacements if we want to monitor large areas at scale and provide early warnings of anomalous behaviors of infrastructures to the local authorities or the infrastructure owners, or spot high-risk area due to their ground displacements. The way to achieve this is through machine learning technologies, which have risen on the last decades as the solution for performing these monitoring tasks at scale. And more specifically, deep learning technologies, they provide state-of-the-art result in a large variety of these machine learning problems. This, together with high-performance computing, is what will allow us to process large amount of data automatically to assess the health of infrastructures at scale. So our first approach was to use a deep learning architecture, which is called deep temporal clustering. This deep learning architecture is what it does is perform unsupervised clustering. What it's going to do, we are going to provide this architecture with some data, and it is going to separate the different time series into different classes in an unsupervised way. We follow this unsupervised approach because usually you don't have ground truth information on over large areas to do it in a supervised way. So we had to go in an unsupervised way. The architecture consists on an autoencoder which learns low-dimensional spatiotemporal features, and then we use these low-dimensional spatiotemporal features to perform the clustering in an unsupervised and non-parametrical way. We to evaluate this methodology, we perform experiments over two different areas of study. On the left hand, we can see over central London. On the left one, we can see the Battersea Power Station area where there have been some dewatering activities, and there is some subsidence in the region that is observable from the space. And then we have another more complex scenario where there are many different events happening, which is in the center of London, in the region of the city. Regarding the Battersea Power Station case study, these are the velocity maps for, in the case of TerraSAR-X data and also Sentinel-1 data. In this map shows the average displacement over a year in average for each point. So we can observe that on the central region, there are some points in which we have a subsidence up to -14 millimeters per year due to these the watering activities that I mentioned. And we can observe that using both satellites, both sensors, Sentinel-1, TerraSAR-X, we can get similar results. When we applied or proposed deep temporal clustering methodology, even though we set the number of classes to detect to n equal to 5, what happens is that the algorithm automatically detected only 2 classes in this. It set automatically the number of classes to 2. It provided only 2 classes, the purple and the yellow. If we compare with the velocity map, the purple correspond to those points with a significant subsidence on the area, and the yellow correspond to points where there is no significant subsidence. So it is effective, for instance, for detecting like ground displacements on the ground. But also we wanted to use this technology in more complex environment, not only like this very simple example. So in this case, this area of study of the city of London, we have many things going on. For instance, on the right, we have in the Bank Metro station, there have been some tunneling activities over the period analyzed. On the right hand, you can observe the in the line correspond to the average of the of the points, and the shadow, it's the standard deviation. Each color corresponds to each different color on the left-hand figure. So, for instance, in this blue class, we can observe that at the end of 2017, it started to observe a negative displacement due to the settlement of these tunneling activities. Then the red class, we can observe that it corresponds to positive displacements. Then we have the green class, which are points over the Black-First bridge, which has a very strong thermal dilation and construction component, and we can observe displacements positive in summer and negative on winter due to the seasonal changes in temperature. And then finally, we have another seasonal component. In this case, it corresponds to structures that are for both docking platforms on the river. And in this case, it's also a seasonal pattern, but in this case, it's opposite at the previous one. In this case, we have positive displacements on winter and negative displacements on summer. So it's opposite to the one that we observe on the Black-First bridge. These are the results that we obtain, and after applying our unsupervised approach over this data set, we can observe that on the region of the bank metro station, it's marked in this dark blue class, and this dark blue class corresponds to a class which started with negative displacements in the end of 2017. Then we can observe that it has detected the red class, which corresponds to positive displacements. Then we have in cyan color, this like blue colors, which is mainly located along the Black-First bridge, and it is a seasonal signal with the positive displacements on summer and negative on winter, which correspond to the dilation and construction pattern that we observe on this bridge. Then we have the yellow class, which is also a seasonal pattern which is inverse to the previous pattern, and it is also mainly located over the docking platforms over the river. And finally, we have another class which is basically flat, and it corresponds to background signal. So this demonstrates that we can use this approach to detect the different patterns of the different phenomena that are going on the region. However, in order to get this result, we need to perform an analysis of what does it mean each class after we perform the analysis. So in order to circumvent this issue, we propose a supervised methodology in which, in this case, because we don't have ground truth labels for ground truth information to perform a supervised approach, what we are going to do is to generate synthetically different patterns corresponding to different phenomena that we want to study. For instance, in this case, we generated 5 different classes of patterns. On the top left, we can see some samples of patterns with positive displacements. On the top right, with negative displacement. On the bottom left, in this case we have positive displacement, but we generated patterns in which the displacement happened very abruptly and very suddenly in a short period of time. So we call this class positive abrupt. And then on the top right, we have the same, but for a negative abrupt patterns. And finally, on the right, we have a thermal pattern that we generated using temperatures from different years. So we are going to train our network with these synthetically generated patterns so that we can apply this approach to detect those patterns on the ground. So, for instance, this is the result that we obtained with this supervised approach. In this case, it detected with the negative abrupt pattern the region around the bank metro station where the tunneling activities were performed. However, the problem of this methodology is that you are only being able to detect those things that you have pre-trained your network. So if there is something else that you are not aware of going on, you won't be able to see it. So these are some limitations of the deep learning approach that we are proposing. The first limitation is that it requires big amounts of labeled data that they are hard to obtain and not available in many cases. In the case of the unsupervised clustering, what happens is that after you perform the analysis, you need to do a manual evaluation of what does it mean each of the different clusters. And in the case of supervised approach, what is going to happen is that you will only be able to detect those patterns that you have defined beforehand. So you may be able to miss some other events that are going on that you haven't trained your network for detecting that. And finally, the last limitation is that in the case of classification, what you obtain is just a qualitative result, but not a quantitative analysis. When you get, for instance, the class with the subsidence, you see that, yes, there is some subsidence in these points, but you cannot, it doesn't give you like how much is this subsidence, it is enough, it is a small subsidence. You know, this qualitative and quantitative analysis is not performed on this. So in order to overcome all these limitations, we also propose another approach in which we use a linear mixture model. Here, what we are proposing is that we are going to model the different time series as a linear combination of some general temporal patterns. For instance, imagine that you have a bridge. This bridge may be affected by different phenomena. For instance, in this case, it's thermal, which is a typical seasonal pattern of dilation and construction. And then, for instance, you may have a little bit of a score, which promotes like negative displacements constantly over time. So what we are going to observe on the bridge is a mixture of the two of the pattern associated to the different phenomena. We are going to assume that this mixture, it happens in a linear way. So we are going to get something like, we are going to multiply the proportion or abundance of the first thermal component plus the multiplication of the proportion or abundance of the second pattern, which corresponds to the scores, and we sum this, obtaining the final linear combination result. So mathematically, it would be like this. In this case, we have a matrix Y, which contains all the different data points that we have by column. So this matrix is L times N, where L is the number of different time acquisition, and N is the number of points that we have on our data set. This matrix is going to be a multiplication of a matrix that contains all the different general patterns, M, which is L times P, where L is the number of acquisition in time, and P is the number of general patterns that are present on the data. And then the matrix A corresponds to the abundances or proportions. So we have the abundances associated to each of the different general patterns. So this matrix is P times N, which is the number of points that we have on the data. Then we have matrix N, which accounts for noise related to the acquisition or maybe atmospheric, which is very common on these kind of images. And also we are going to consider the non-negativity constraint. We are going to consider only positive proportions or positive abundances. This is because imagine that if you have a pattern in which we have positive displacements, and then we have another pattern in which we have negative displacements. If we don't consider only positive abundances, what is going to have that these two patterns may be detected at one pattern, but In the case of positive displacements, the abundances are going to be positive, but in the case of the negative displacement, it's going to be the same pattern, but with negative displacement. And this is not very intuitive. And also because if you have one pattern with positive displacements and another pattern with negative displacement, usually these are going to be two patterns related to two different phenomena. So these two different phenomena, maybe you want to detect as different and separate, totally different and separate patterns. So that's why we introduced this positivity constraint on the abundances. So in order to solve this problem, we use this blind sparse separation algorithm. What we are going to do is to minimize this function with regards to M and A. The first term is a data term, and then the second term is the L1 norm over the abundances. This term promotes sparse solutions on the abundances. What is going to happen is that for each point, is not going to be affected by all the phenomena at the same time. It's going to be affected only by 2 or 3 or very reduced number of phenomena at the same time. So that's why this matrix is going to be sparse, and we promote sparse solution with this term. And also it is also very good because it prevents noise overfitting, so it works really well with noise, which is the case of this multi-temporal InSAR data. Another constraint that we are enforcing is that our patterns, general patterns MI, are going to be normalized to the unit. This is because if we normalize all the patterns to the unit, then we will be able to compare directly the abundances and compare how big or small are the displacement directly comparing the abundances. Otherwise, if we don't normalize the different patterns to the unit, what's going to happen is we have to take into account the norm of the pattern and also the size of the abundance. So this is also for convenience. And in order to evaluate this method, we generated a set of synthetic data. We use 16 temporal patterns extracted from real InSAR, multi-temporal InSAR data, and we use it as our matrix M. Then for the abundances, we generated procedurally some spatial patterns, and then we generate mixtures over these different abundance maps with using a Gaussian filter. So at the bottom left and at the bottom, you can see the two different scenarios. On the left hand is the synthetic one dataset. In this scenario, the mixtures are much lower. You can see that there are places where each of the images correspond to each of the different pattern. So you can see that there are totally yellow points, which means that there is only one pattern on that place. However, on the case of the synthetic dataset 2, you can see that it is much more mixed. So you can see that you don't have totally yellow points. The points are light blue or green. This means that the abundances are maximum 0.7, which means like 70% of something, and then there is only another 30% of something else. So this second scenario is much more heavily mixed and is much more complicated than the first scenario, where you have some points in which you only have one pattern. Then we also simulate environmental noise using Gaussian noise, and also we added real noise in other case, extracted from real multi-temporal InSAR data. So these are some examples of the output result. This one particular example after multiplying the time series patterns times the abundances, and this is for one particular time acquisition. After adding the noise, the result that we will obtain. And then for simulating the phase inconsistencies, because in InSAR data, because not every point reflects the signal, you will get a sparse set of points where you get the time series, but there are other points where you don't get anything. To simulate this behavior of multi-temporal InSAR data, we just random samples on the different pixels on space. So these are some results obtained in the case of the synthetic one dataset. In this case, as we mentioned, because in this case we have points which only contains one pattern, what is going to happen is that in this figure you can see in blue is the closer pixel to the pure pattern with noise. In red is the closer pixel on the image to the ground truth pattern without noise. In yellow is our estimation of the ground truth pattern, and in purple is the ground truth pattern. So because in this scenario we have pixels that only contains one ground truth pattern, it is the same, the ground truth pattern and with and without noise, the ground truth pattern with the pixel without noise. So in this case, it's everything the same. In the case that we add noise, we can see that our estimation is noise-free. So this means that our method, it works very well in the case of noise condition, and then it is very similar to the ground truth and the pixel without noise. So this is very good result. In this second case, because we mentioned that this scenario is much more mixed scenario, what is going to happen is that the ground truth pattern doesn't correspond with the pixel without noise, because this pixel without noise is maybe 70% pure, but there are maybe 30% of some other pattern. So our estimated ground truth pattern, it is also good estimation because it's closer to the ground truth pattern than the more close pixel to the ground truth pattern that are in the data. So this is also really good example that our estimation is good. And then on the right we have the same, but in this case we have very heavily noise. And nevertheless, we have very heavy noise. In this case, we can see that we can obtain a very good estimation without noise. So this is also a good result. Finally, on this case is the case in which we added real noise extracted from real multi-temporal InSAR data. In this case, in the previous case, the noise was Gaussian, so it's equally distributed along time and along all the pixels. But in this case, because it is real noise, maybe it's not equally distributed. The distribution of the noise is not equal, which is much more complicated to deal with. But even though we observe also that our estimation is close to the ground truth pattern, so it's also good result. And then on the right side, we can see a comparison between our method, which is this one in green, which is BSSS, stands for blind sparse separation, which is our method, compared to other different algorithms, which are BCA, MFinder, ATGP, and CSAT. These other algorithms, they solve a similar problem that we are solving, but they were applied to hyperspectral images. So let's say that they were designed to work in other conditions, but the problem that they are solving is basically very similar. So that's why we are using for comparison. And here we can observe that this is cumulative error a long time. So the lower the better. And we can observe that in our case is better than all these other algorithms. This is also a comparison between all these algorithms, and on the last column is our proposed method. We also added to this comparison PCA, principal components analysis, and ICA, independent component analysis, just for comparison. The numbers correspond to the average cosine distance between the estimated patterns and the ground truth patterns. So these numbers are error measurements, so the lower the better. And we can observe that in the case of synthetic 1 dataset, or this is for different levels of noise. So for different levels of noise in the synthetic 1 case, our algorithm provides the better result in all cases. In the case of the synthetic 2 dataset, our algorithm provides the best result in the case of heavily noise of 5 dBs and 10 dBs of signal to noise ratio, and also in the case of real noise. In the case of lower noise, there is another algorithm that is better than ours. This is because this other algorithm is very specialized on scenarios that in which we have heavily mixed mixtures, which is the case of this synthetic 2 dataset. But because on InSAR data, we typically have very strong noise component due to the atmospheric factors. In real scenarios, it's better our approach. So finally, this is again an analysis over the region of the city in central London. We wanted to check how works this proposed methodology in a real scenario. So that's why we use this study case. Here we can observe the pattern extracted that correspond to the bank metro station tunneling activities. Here we can see clearly that at the end of 2017, there is a clear negative displacements due to these tunneling activities, and on the left hand side we can see the abundances or proportions related to this temporal pattern, and we can see that in this case what we obtain is a quantitative measurement, not as we had it before with the classification that you only get a class label. In this case you get a measurement of how severe is the abundance regarding to this pattern. So you can use this information to measure the displacements and how severe are the displacements on this region due to the settlement. So this is much more useful and much more informative result than the previous classification result. This is again another pattern that is related to the positive displacements in these two areas. Then we can observe here another pattern that has been extracted that correspond to the black first bridge, and we can observe in which point this thermal component is much more strong or not. And here we can see that the pattern corresponds to positive displacement on summer and negative on winter due to temperature seasonal changes. And finally, this is another seasonal pattern extracted, which correspond to the boat docking platforms. We can see that the pattern is also seasonal, but in this case, it's the opposite, is positive displacements on winter and negative displacements on summer. And we can see that it's clearly corresponding to these platforms over the river. And that's the results that I got. In conclusion, we have seen that deep learning technology can automatically learn to differentiate between different temporal patterns, but they have some limitations. We have proposed a blind source separation technique that is able to detect different temporal patterns associated to the different phenomena that are happening on the scene. And also, this proposed methodology is based on the linear mixture model that can characterize the different temporal behavior as a mixture of different patterns associated to the different phenomena. This methodology allows us not only to locate where the different phenomena are happening, but also to quantify how severe are these displacements with these abundance maps that I showed you before. And also, furthermore, it deals really well with the highly noise atmospheric conditions that typically are present on multitemporal InSAR data, which is one of the main problems when you try to analyze this type of data, is that you have a strong contribution for atmospheric conditions and the data is highly noisy. So it deals really well in this situation. So these are the conclusions of this talk. Thank you very much for your attention, and now I will be pleased to answer all your questions.